Okay, welcome back to P3. We're in the topic called conservation of energy. I'm going to start off with these two equations here, okay? The first one is gravitational potential energy. It's equal to the mass times the gravitational field strength times the height, okay? Second one is the kinetic energy, which is half times the mass times the velocity squared. Here are the respective units. In your exams, you've got to be able to rearrange these equations, okay, to find one of the unknowns. It's important to note as well that G on the Earth is 10 meters per second squared. Okay, so please make a note of that. The units can also be newtons per kilogram, but just bear in mind that G on the planet Earth is 10. Okay. Next thing we're going to be looking at are what we call Sankey diagrams. Okay, so if we look at this energy input here, notice there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 small boxes. Okay, and there's 4 small boxes here, and there are 6 small boxes here, which means this is 60% efficient. Okay, we've got 6 small boxes of the useful energy being outputted, and we've got 4 small boxes. That's 40% of the energy of the original input energy being wasted. Okay, so these are what we call Sankey diagrams, and bear in mind, please make sure that the useful energy just literally goes horizontally across and any wasted energy goes downwards. Okay, and make sure that the width of your respective arrows are in accordance with the percentage of energy wasted and the energy used, the useful energy outputted as well. Okay. Just generally, okay, you should know about the idea of the conservation of energy, okay, which states that energy can never be lost. It can only be converted from one form to another, okay? So in this particular case, we've got the original input energy being converted into some useful and some waste. Okay, so let's look at some of those types of energy. So we've got magnetic potential energy. So this is the energy stored in the magnetic field around a bar magnet or a solenoid or an electromagnet. We also have got gravitational potential energy, which is essentially the energy stored between two bodies. So for example, ourselves and the Earth. So the higher up we go, according to this equation, we've got more gravitational potential energy that will get released if we fall to the ground. We've also got elastic potential energy or strain energy. So this is the energy stored in a rubber band when we stretch it before we release it. Kinetic energy, an example, would just be simply walking. So the energy is present in the person walking. Okay, so it doesn't go anywhere. So it's stored within the human that's walking. Although kinetic energy does mean movement. Okay, moving energy. Chemical energy is the energy stored in food or fossil fuels. Okay, that gets released when we obviously respire, or when we move about, when we speak, when we talk, and fossil fuels in power stations as well, when they heat up some water and then turn a turbine and so on. Electrical energy is basically the flow of charge, so the fact that we have electricity in circuits, okay, that basically that energy follows the electrons, so it doesn't go anywhere. Thermal energy, basically in liquids, solids and gases, we can look at the thermal energy being present in the respective states of matter, okay, not going anywhere. However, we know that heat can be transferred through heating, okay, so that's one way that energy can be transferred. And finally, for the last energy store, it is nuclear energy. So this is the energy stored within the nucleus of atoms, okay? And we find out about nuclear fission and fusion in a later unit, where lots of energy gets released when atoms split up or nuclei join together. Okay, so energy can be transferred mechanically, so that's literally just moving objects about, okay, so throwing a ball or something like that. Light through light as well. Remember, light is a wave, so we have electromagnetic waves or the EM spectrum, where essentially we can have radio waves being sent across the sky, or microwaves and other types of waves in the EM spectrum, where energy gets transferred from one point to another without the actual matter being moved, okay, between the 2 points. We can also get energy being transferred electrically, okay, so that's when the electrons pass on their electrical energy onto, for example, a lamp, which then that energy gets converted into light energy and a bit of thermal energy. We can also get energy being transferred via a sound wave. Remember, waves transfer energy without the matter actually moving from point A to point B. Okay, so let's look at the next point. So, simple law of conservation: energy cannot be created or destroyed, as I've said before. Okay, so in terms of the Sankey diagrams, just ensure that you're always confident with this point, okay, that we cannot get any energy wasted that is unaccounted for, okay. All the original input energy has to either be outputted as a type of useful energy or multiple types of useful energies and multiple types of wasted energies. What does wasted energy generally do? Okay, it can warm the surroundings, or it can cause sound pollution if that's one of the types of energy you're not interested in, okay? Okay, so eventually all energy will be sent to the surroundings. Right, to prevent heat loss, we use thermal insulation. Examples of thermal insulation at home is basically loft insulation, okay, cavity wall insulation, thick curtains, double glazed windows, okay. Please ensure you're at least confident with listing some of these examples where you can reduce the amount of energy or thermal energy loss at home, okay. So what would reducing heat loss do to the efficiency? Well, it would increase it, okay? So a cup of hot tea left in a room while cooling will eventually reach room temperature. How do we decrease the rate of cooling? We can add some insulation. How do we increase the rate of cooling? Well, basically just remove the insulation and open up the lid, okay? Other thing you need to be aware of, thermal conductivity. So if a material is a really good thermal conductor, okay, obviously the rate of cooling will increase because the heat transfer in that particular material will be very quick. This next equation you need to know as well. Very, very simple, very straightforward. Efficiency is equal to the useful energy output divided by the total energy input. So if I go back to our Sankey diagrams, that means it's this energy divided by our total input. And sometimes you can times by 1,000 if you want that in a percentage form. Okay. Again, efficiency will always be less than 1. Okay, unless it's 100% efficient, which is very rarely the case, because in real life we do not have 100% efficient devices. Okay. Common exam questions ask you, how do you reduce friction? Okay. Well, one of the things you can do is obviously use some lubrication. Okay, that will reduce the amount of heat lost. If it's a mechanical device or engine, okay, because obviously if we increase the lubrication, we have less friction, therefore less heat wasted. Right, 2 terms you need to be aware of: renewable and non-renewable. Okay, renewable means that the energy resource can be replaced quickly. Okay, non-renewable means that it takes a really, really long time to replace. Okay, so several generations. How do we create electricity? Okay, very, very simply. We're going to use one of our fossil fuels, which are listed here. Okay, they're going to be used to heat up some water. So it obviously cause one of these fossil fuels to combust. Okay, that means the water is going to be heated up. It's going to be in one container, which when water heats up, it will become a gas or vapor. That high pressurized steam will then turn a turbine. Okay, that turbine is then going to be connected to a generator, which will then convert that kinetic rotational movement into electrical energy. We will look at the generator in a later video when we go over that topic, okay? So what is one advantage of using fossil fuels? They are reliable, okay? We know where to find them, okay? We've used them for a very long time, and we've built our national grid, we've built our cities around fossil fuel power stations. However, one disadvantage, okay, is that they're non-renewable. They're eventually going to run out, okay? There's only a certain amount of these natural fossil fuels underneath the ground, okay? And also they produce carbon dioxide and sulfur dioxide, which are very harmful gases to our environment, okay? Cause global warming and just general pollution and acid rain. Right, let's look at nuclear energy. Okay, so nuclear energy is an example of another non-renewable type of energy. Okay, so what happens in a nuclear fission power plants is heavy nuclei, for example uranium, splits up. Okay, and as they split up, they release a huge amount of energy. Okay, which is generally in the form of heat. This then again, in the same way as the fossil fuel power station is going to heat up some water. That high pressurized steam is going to turn a turbine, then a generator, and then we've got electrical energy. It's reliable, okay? It does not give out carbon dioxide or sulfur dioxide. However, the waste is still radioactive, okay? And we've got to put the radioactive waste in designated areas and we've got to ensure it's away from communities of humans. But there is a risk, obviously, if somebody decides to dig up that particular ground, they could be exposed to the radioactive waste. So, and it's also very radioactive for a very, very long time. Okay, so that's one disadvantage. Right, biofuel is anything that is recently been alive, for example, wood, okay, and we just basically heat it up again. Okay, so similar, we can use it to heat up some water, steam turns a turbine, and so on. Now, when we say it's carbon neutral, it means, and we're talking about wood that naturally dies out, okay? It means we're not cutting down more trees, okay, which photosynthesize, okay, as opposed to producing carbon dioxide in our power station. Okay, so it's sort of balanced, unless we're cutting down a lot of trees, which means the intake of carbon dioxide from plants and trees will be lessened because obviously we've taken some of the trees out. We can say it's carbon neutral, okay? It's also renewable because if we're saying it's the natural dead trees that we're just simply using and that we're burning, and that will also obviously give off carbon dioxide when we burn them. That's good for the environment, okay? Because it's all natural. We're not doing anything out of the ordinary, okay? Disadvantage: takes time to grow trees. And also it's also weather dependent, okay, so it's not that reliable. Right, what about wind turbines? It's affected by the weather, okay, we hopefully you should know that. You know, if you've got no wind, we can't turn a turbine, we can't get electricity, okay. However, wind is part of the atmosphere, okay, part of the weather patterns, okay. It's renewable, doesn't give out carbon dioxide. However, it is unreliable. Tidal is when water is basically due to the movement of water from a higher land level compared to a lower land level, okay? And that movement that water movement we can use to turn a turbine and then a generator, okay? So the same principle applies there. It's reliable, happens generally twice a day. So we can say we don't need anything extra, obviously, apart from building the equipment to obviously connect up the generators and the turbines. No carbon dioxide emission as well. However, it's dependent on the location, okay? Because we can't obviously have a tidal power plant on the land. Hydroelectricity, essentially, we need to build these around a dam. Okay, this relies on the water movement. Again, when we've trapped some water and then we let the water get, when it's released, it will pass through some turbines and then that will turn a generator. Okay, it's reliable. Okay, it can be stored as well. So obviously, if there's a need for a lot of energy, we can obviously let some water through and then we can get some energy. It's we can say it's free fuel because we're obviously not, it's part of the environment. Okay, we're not digging into the ground to get anything else. It's renewable as well. However, it does cost a lot of money to set up and sometimes can flood up the local area. Okay. Common exam question. It asks you to give reasons why countries are using less fossil fuels to generate electricity. We've already talked about it. Eventually, how it's going to run out because there's only a certain amount of fossil fuels in the ground. Also, they give out sulfur dioxide and carbon dioxide, which is bad for the environment. Okay. Why is sulfur dioxide bad? Well, rain becomes acidic. Okay. Carbon dioxide traps heat from the sun, causing the Earth's general average temperature to rise. So it adds to the problem of global warming.